Welcome to the deep dive. We've got a really interesting set of materials today, chapters 1 through 9, covering, well, a huge range from geology right through to ecosystems and human impact.
Yeah, quite the journey.
So our mission here is to really unpack the core ideas for you, connect the dots between these chapters, and give you a solid, digestible understanding of these key environmental concepts.
Sounds good. It all starts, really, with the fundamentals of the planet itself.
Exactly. Okay, let's kick things off with chapter 1, starting right from the ground up, rocks and minerals.
Indeed. And what's interesting from the get-go is how these basic building blocks form and how, our need for them triggers this whole chain of events.
Right. Chapter 1 gets into the rock cycle first, this idea that the Earth is constantly changing rocks from one type to another, and the three main types.
You've got igneous rocks, first formed from cooled magma or lava.
Like basalt, that's the extrusive kind, cools quickly on the surface, small crystals.
Right, versus intrusive like granite, which cools slowly underground so you get those larger crystals.
Okay, then number 2.
Sedimentary. These are formed from, sediments, little bits of rock, shells, other materials getting compressed together over time. Think limestone, sandstone.
Shale, too. And the third type is metamorphic.
Exactly. Rocks that have been changed, transformed by heat or pressure, or both.
Yeah.
Marble from limestone, slate from shale. Those are classic examples.
So the Earth is basically recycling its own crust.
Pretty much, yeah.
Right.
And these processes can concentrate minerals into what we call ores, which leads to the next part. How do we find them?
Prospecting. The materials mention remote sensing first, using aerial photos, satellites.
GPS for exact locations.
Mm-hmm.
It's efficient, covers huge areas, works in pretty much any weather.
Then there's geochemical analysis.
Right, taking samples, stream sediments, soil, maybe some shallow drilling, and analyzing the chemistry. Again, GPS is key for mapping where you find interesting results.
And finally, geophysics.
Yeah, using physical properties, like sending seismic waves down and seeing how they bounce back to figure out the structures underground.
Okay, so you found a potential deposit. How do you get it out? Chapter 1 outlines 2 main methods. Surface mining.
Also called open pit or strip mining, used when the deposit is near the surface.
Right. Involves removing the topsoil, vegetation. Sometimes explosives are needed for things like sand, gravel, coal, iron ore.
And the other main type is subsurface mining, underground.
Deep mining, shaft mining. Digging vertical shafts, horizontal tunnels to reach deposits further down, like for gold, diamonds.
Big difference in approach and visual impact, too. Subsurface leaves those waste heaps on the surface.
Definitely. But deciding whether to mine, that's complex. It's not just, is the ore there?
Not at all. Exploration costs money, obviously. Then the geology itself. Is it high-grade ore, meaning lots of mineral, or low-grade? How deep is it? How much rock and soil? The overburden is on top.
Accessibility is another one. Transport costs, infrastructure. Can you actually get the stuff out and to market easily?
And crucially, the environmental impact assessment. You need one for a license. It looks at habitat loss, how you restore the land afterwards, waste disposal.
And finally, simple economic supply and demand. Is it actually worth the cost to extract right now?
Market forces, yeah. It all has to add up.
Now, the environmental impacts. Chapter 1 is pretty clear here. Habitat loss is a big one, often involving deforestation.
Huge. And pollution comes in many forms. Noise from the operations.
Water pollution is a major concern. Acid mine drainage, toxic metals leaching out, sometimes even lowering the local water table.
Land pollution from the waste heaps, air pollution from dust, even just the visual blight on the landscape.
Plus managing all that waste and the risk of erosion once vegetation is removed.
There are economic impacts too, of course, jobs, money coming into the area.
Yeah.
But it can make the land useless for farming.
And social aspects, maybe new infrastructure, but also major concerns about worker safety in mining.
It really highlights that trade-off between resource needs and environmental, damage.
So how do we manage these impacts? The chapter mentions a few strategies, increasing efficiency, for one.
Yeah, getting more out of the ore you mine, maybe reprocessing waste, and using less material in products in the first place.
Recycling is huge, too. Reduces the need for new mining, saves energy, less waste.
Legislation plays a big role, setting standards, making companies responsible for cleanup and recycling.
Waste management techniques like landfilling or sanitary landfilling, which is more controlled, and bioremediation.
Using living organisms like bacteria to break down or neutralize pollutants can sometimes be done right there, in situ.
And finally, land restoration. trying to fix the damage afterwards.
Improving the soil, planting trees, maybe creating nature reserves or even lakes in the old pits if they're lined properly and non-toxic.
It all ties into that idea of sustainable use, sustainable development, meeting our needs now without messing things up for the future.
Exactly, which is a good transition into Chapter 2, Energy and the Environment.
Right. How we power our world. It starts with fossil fuels. Where did they come from?
Well, coal formed mainly from ancient land plants getting buried, compressed, and heated over millions of years. Peat is sort of the first stage,
And oil and natural gas.
mostly from tiny marine organisms. They died, sank, got buried under sediment without oxygen anaerobic decay, and then heat and pressure transformed them over geological time.
Knowing that origin is key because getting them out and burning them has such big environmental consequences.
Definitely. And the main way we use them, in biofuels too, is for electricity,
The basic process is burning the fuel to heat water.
which makes steam. The steam turns a turbine, and the turbine spins a generator to make electricity. Pretty standard process for thermal power plants.
Nuclear power also uses heat to make steam, but the heat comes from nuclear fission, splitting uranium atoms.
Right. But then we get into the renewables, the alternative. Solar power is a big one.
Using photovoltaic cells for electricity or solar heating panels for hot water. The catch, of course, is it only works during daylight hours, and panels can have a visual impact.
Wind power, using turbines. Highly dependent on location, you need enough wind, and they also have visual impacts and take up quite a bit of land.
Wave power is mentioned, using ocean waves to drive turbines. Hydroelectric power.
Using dams on rivers, creates a reservoir, water flows through turbines, no CO2 emissions during operation, but huge impacts on river flow, ecosystems, fish migration.
And geothermal tapping into the Earth's own heat.
Clean source, but expensive to set up, and really only feasible in specific areas with geological heat near the surface.
So choosing which energy source to use involves balancing a lot of factors.
Absolutely. Economics is one. Is there a local supply? What's the upfront investment cost, especially for renewables?
Social factors, too, impact on existing industries, like coal mining versus new jobs in renewable tech.
And a big one, environmental impacts. Pollution, carbon emissions, habitat destruction.
The materials sort of lay out the pros and cons: fossil fuels, established tech, jobs, but pollution and finite supply. Nuclear, no CO2, but radioactive waste.
Biomass, renewable but land use issues, can impact ecosystems. Geothermal, clean, unlimited, but costly and geographically limited.
Clean water management benefits, but impacts rivers. Solar, renewable but daylight dependent, visual impact. Wind, renewable but location dependent, visual impact, land use.
It seems like relying on just one type has drawbacks. Do the materials suggest combining renewables?
It doesn't explicitly detail combination strategies, but it does lead into why we demand so much energy. Domestic use is a big part: heating, cooling, appliances. Influenced by cost, availability, even social status.
Industrial demand for manufacturing. Transport heavily reliant on fossil fuels for moving goods globally.
Personal and national wealth. As economies grow, people tend to use more energy, buy more energy-consuming things.
And climate itself. Colder places need more heating, hotter places more cooling, places with less daylight need more lighting. Climate change itself is starting to increase demand too, ironically.
Given all that demand, conservation and better management are vital.
Yeah. Chapter 2 lists several approaches. Reducing how much we use in the first place. Insulation is key for buildings, loft, walls, floors, better windows, stopping drafts.
Increasing efficiency. Choosing appliances with good energy ratings, using smart meters to track usage, driving more fuel-efficient cars.
Governments have a role too. Setting stricter building codes, maybe banning very inefficient devices, offering incentives for things like insulation or trading in old cars.
And really pushing to use the renewable resources we have, maybe keeping fossil fuels just as a backup for when the sun isn't shining or the wind isn't blowing.
Plus, smarter transport policies, investing in public transport, making cycling safer, restricting cars in city centers, managing parking.
Okay, moving on to Chapter 3, Agriculture and the Environment. This starts right down in the dirt-soil composition.
That mix of minerals, organic matter, water, and air. The proportions vary a lot depending on the soil type, climate, how it's managed.
And particle size makes a difference. Sand is gritty, silt, silky, clay sticky.
And soil is absolutely fundamental for plants. It provides nutrients.
Like nitrogen, phosphorus, potassium, the big three.
Right. And water, anchorage for roots, oxygen for respiration in the roots.
Organic matter is crucial too. And the decomposers living in the soil, earthworms mixing things up, fungi helping nutrient uptake, bacteria converting nitrogen.
High organic matter is great. holds water better, improves aeration and drainage, feeds decomposers, holds on to nutrients.
Soil pH acidity or alkalinity matters too, influenced by the rock it came from, rainwater. Farmers sometimes adjust it.
Yeah, adding lime makes it less acidic. Some fertilizers can make it more acidic. Plants have preferred pH ranges.
The chapter contrasts sandy and clay soils. Sandy drains well, easy to work, warms up fast, but doesn't hold water or nutrients well.
Clay is the opposite, holds water and nutrients well, but can get waterlogged, poor drainage, hard to cultivate, slow to warm up. So things like drainage, how easy it is to cultivate, water holding capacity, all depend on that mix.
Then we get into the different types of agriculture. Arable is crops, pastoral is animals.
Mixed is both. Subsistence farming is mainly for the farmer's own family, like shifting cultivation or traditional wet rice farming.
Commercial farming is about selling the produce, tea, coffee, large-scale rice.
And there's extensive versus intensive. Extensive uses large areas, low inputs per area. Intensive aims for high output from smaller areas, usually with high inputs, fertilizers, pesticides, etc.
To get those high yields, especially in intensive farming, various techniques are used. Crop rotation is one.
Yeah, changing crops each season helps control pests and diseases that target specific crops, and manages soil nutrients better, maybe including legumes to add nitrogen.
Fertilizers, obviously. Adding those mineral nutrients back into the soil. Organic like manure or inorganic chemical fertilizers needs careful use, though.
Irrigation, getting water to the crops.
Yeah.
Essential for nutrient uptake. Different methods like overhead sprinklers or more water-efficient trickle-drip systems.
Controlling competitors, weeds, pests, diseases, using herbicides, insecticides, fungicides, or sometimes biological control using natural predators.
Selective breeding over generations to improve crop yields or animal characteristics, and more recently, genetically modified organisms, GMOs.
And controlled environments, greenhouses where you manage temperature, light, CO2, or hydroponics.
Growing plants without soil, just using water with dissolved nutrients, can be very efficient, uses less space, but it's complex and costly.
Okay, chapter 4 shifts to water, a hugely important resource. Where is it all?
Well, the vast majority, 97%, is salty ocean water, covering about 75% of the surface. Only about 3% is fresh water.
And most of that fresh water is locked up in ice caps and glaciers.
Yeah, about 2/3 of it. Most of the rest is groundwater. Lakes, rivers, the atmosphere hold relatively tiny amounts.
Understanding the water cycle is key to managing it. Evaporation from surfaces, transpiration from plants.
Together, that's evapotranspiration. Water vapor rises, cools, condenses into clouds, then falls as precipitation rain, snow, hail.
Vegetation plays a big role in surface rain, increases infiltration into the soil, reduces surface runoff.
Water then flows through the soil through flow, or deeper down as groundwater flow, eventually making its way back to rivers and oceans. Percolation is the deeper movement.
So where do we get our usable water from?
Surface water is a big one. Lakes, rivers, swamps. Aquifers, those underground layers of rock holding water access via wells.
Sometimes artesian aquifers, where water is under pressure. Rivers themselves, obviously. Reservoirs created by dams.
Desalination plants, turning seawater into fresh water, mainly in coastal arid regions, and even snowmelt from mountains.
And we use water for everything: domestic uses like drinking and cleaning, industry for cooling or manufacturing, and agriculture is a huge user for irrigation and livestock.
The availability and quality vary massively around the world. You have water-rich places like Canada or the Amazon basin.
Contrasting with water-poor regions like deserts in Australia or Sudan, this scarcity can lead to conflict.
And disparities between cities and rural areas even within countries.
Dams are often built as multi-purpose projects.
Yeah, controlling floods, storing water for irrigation or drinking, generating hydroelectricity, improving navigation, sometimes recreation or fish farming.
But building a dam involves huge considerations: choosing the right site, rainfall patterns, geology, valley shape, hydropower potential, proximity to users, avoiding pollution sources.
The environmental impacts can be massive: flooding habitats to create the reservoir, changing the river flow downstream, trapping silt, blocking fish migration.
Economic costs versus benefits. Social impacts like displacing communities versus the benefits the dam provides.
And long-term sustainability of reservoirs eventually silt up, and there's always the risk, however small, of dam failure.
Water pollution is another major theme in this chapter. Where does it come from?
Lots of sources: domestic sewage carrying pathogens, nitrates, phosphates, industrial waste, toxic chemicals, heavy metals.
Agricultural runoff, fertilizers, pesticides, animal waste, even things like nuclear waste or oil spills from offshore drilling.
And the impact is severe. Leads to inequalities in access to safe water, waterborne diseases like cholera and typhoid.
Toxic substances can build up in the water, kill aquatic life. Bioaccumulation and biomagnification.
Right, where toxins like mercury or pesticides get more concentrated as you go up the food chain.
Acid rain effects on lakes and rivers. And eutrophication.
That's when excess nutrients, often from sewage or fertilizers, cause algal blooms. When the algae die and decompose, it uses up oxygen, creating dead zones.
So how do we manage this pollution?
Improved sanitation is fundamental, separating sewage from drinking water, proper toilets, sewage treatment systems.
Sewage treatment itself involves stages: primary, removing solids; secondary, breaking down organic matter biologically; tertiary, filtering and disinfecting.
And treating water to make it drinkable, aeration; screening, letting sediment settle; adding chemicals to clump particles; coagulation; filtering; chlorination, maybe adding fluoride; then storage.
Pollution control laws are essential too. Monitoring water quality, setting limits on discharges, international agreements like for the Great Lakes, fines for polluters.
And managing specific water-related diseases. For waterborne ones like cholera, it's about clean water, sanitation, hygiene. For waterbred ones like malaria.
Where mosquitoes breed in stagnant water, it's about controlling mosquito populations, preventing bites, and treating infected people.
Okay, Chapter 5 moves us out to the oceans and fisheries.
Oceans as a resource: food, obviously fish, but also chemicals, building materials like sand and gravel, potentially energy from waves or tides, tourism, transport.
And maybe more drinking water via desalination in the future.
Where are the world's main fisheries located?
They're strongly linked to ocean currents and nutrient availability. Fish tend to congregate on the continental shelves, the shallower areas near coasts.
Why there?
Because there's enough sunlight penetration in the euphotic zone, down to maybe 200 meters, for phytoplankton to grow. Phytoplankton are the base of the food web. They also need nutrients, often brought up from deeper waters by currents, upwelling.
The chapter mentions El Niño's impact on the Peruvian anchovy fishery.
Yeah, a classic example. During El Niño, warm, nutrient-poor water replaces the usual cold, nutrient-rich upwelling off Peru. The phytoplankton die off, and so do the anchovies that feed on them, or they migrate away. Massive impact on the fishery.
So how does our exploitation affect the oceans? Overfishing is the big one.
Driven by global demand. It impacts the target species, obviously, but also bycatch all the other unwanted stuff caught in nets.
Things like fish aggregation devices, FADs, attract lots of species, not just the target ones. Trawl nets dragging the bottom can be very destructive.
Whereas methods like pole and line are much more selective. Mesh size in nets is also critical. Small mesh catches young fish before they can breed.
Aquaculture, or fish farming, is mentioned as a way to potentially reduce pressure on wild stocks.
It can help, yes, though it has its own environmental issues to manage.
So how do we manage wild fisheries more sustainably?
Regulations on gear are important: net types, mesh sizes, like using square mesh panels that let smaller fish escape, promoting selective methods.
Setting quotas limits on how much of each species can be caught, based on scientific assessments.
Closed seasons to protect fish during breeding times. Establishing marine protected areas or reserves where fishing is limited or banned.
Conservation laws, international agreements like the Law of the Sea, UNCLOS, which established exclusive economic zones, EEs, where coastal nations are responsible for managing resources.
But enforcing all this is really hard. The oceans are vast. Monitoring is difficult and expensive.
There are strong incentives for illegal fishing. People try to get around quotas. Authorities are often under-resourced.
Yeah, it's a massive challenge to make these management strategies truly effective everywhere.
Okay, Chapter 6 brings us back to land, mostly dealing with natural hazards, starting with the Earth's structure.
Right. The thin outer crust, denser oceanic crust, lighter continental crust. Then the mantle below that, and the core at the center, liquid outer core, solid inner core.
And plate tectonics explains a lot of these hazards. The idea that the crust and upper mantle, the lithosphere, are broken into plates moving around on the mantle.
Driven by convection currents in the mantle. Where plates move apart, divergent boundaries, magma rises, you get volcanoes, often shield volcanoes, and rift valleys.
Where they collide convergent boundaries, one plate might slide under the other, subduction. This creates mountains, volcanoes, often more explosive composite ones, and earthquakes.
And where they slide past each other, conservative boundaries, you get earthquakes, like along the San Andreas Fault.
Earthquakes themselves, the shaking caused by released energy, magnitude measured on the Richter scale, which is logarithmic.
So magnitude 7 is 10 times bigger amplitude waves than a 6, and releases about 32 times more energy. The focus is the underground origin point. The epicenter is the point on the surface directly above.
Earthquakes cause seismic waves, can trigger landslides, liquefaction where wet ground acts like liquid.
Aftershocks and tsunamis if the quake is under the sea. The impact really depends on where the epicenter is relative to people and buildings.
Volcanoes vents where magma erupts. Signs like ground temperature changes or gas emissions can sometimes give warnings.
Then there are weather-related hazards. Tropical cyclones, hurricanes, typhoons, intense low-pressure systems forming over warm ocean water near the equator.
Flooding caused by heavy rain, snowmelt, storm surges, tsunamis, even urbanization, increasing runoff.
Drought, prolonged lack of rain, can be linked to high-pressure systems, weather patterns like El Niño, La Niña, and climate changes making them worse in some areas.
The impacts of all these hazards are immense. Tectonic events, damage, fires, tsunamis, landslides, habitat loss, disease, death, huge financial costs.
Tropical cyclones, wind damage, flooding, death, disease, flooding, death, crop livestock loss, infrastructure damage, contamination, disease.
Drought, water shortages, crop failure, starvation, soil erosion, desertification, poor air quality, wildfires.
So managing them involves prediction, preparation, and response. For earthquakes and volcanoes, monitoring seismic activity, ground deformation, gas emissions.
Preparation includes things like land use zoning, don't build on fault lines,
Yep.
earthquake-proof building codes, disaster plans, hazard maps, maybe lava diversion for volcanoes.
During and after. Evacuation, rescue, aid, rebuilding.
For cyclones, satellite tracking for prediction. Preparation includes building codes, shelters, maybe coastal defenses like embankments or preserving mangroves. Evacuation is key.
Flooding. Monitoring rainfall and river levels. Creating flood maps. Preparation like sandbagging, shelters. Response involves rescue and rebuilding. Drought. Monitoring rainfall, managing water supplies with dams, wells, water transfer, desalination, conservation measures, providing aid.
Interestingly, the chapter also notes that hazards can sometimes offer opportunities.
Yeah, rivers provide fertile floodplains, water transport. Volcanoes create fertile soil eventually, geothermal energy, mineral deposits, tourism.
And people live in hazardous areas for family reasons, jobs, or because they feel they have no other choice.
Right. Okay, Chapter 7 moves up into the atmosphere and human impacts there.
Starting with the atmosphere's troposphere, weather layer, stratosphere with the ozone layer, mesosphere, thermosphere.
And its composition mostly nitrogen and oxygen, small amounts of argon, water vapor, and trace gases like carbon dioxide. The natural greenhouse effect is crucial gases trapping heat to keep the planet warm enough for life.
But human activities are causing pollution. Smog, that hazy pollution in cities, often from vehicle emissions reacting with sunlight, trapped by inversions.
Acid rain, sulfur dioxide, and nitrogen oxides from burning fossil fuels reacting with water vapor. Damages lakes, forests, buildings.
Ozone depletion, caused mainly by CFCs released from old aerosols and refrigerants, thinning the protective ozone layer in the stratosphere.
And the enhanced greenhouse effect, adding extra greenhouse gases like CO2 from burning fossil fuels, deforestation, methane from agriculture waste, CFCs, nitrogen oxides from vehicles, fertilizers. This is driving climate change.
The impacts are serious. Smog causes respiratory problems. Acid rain harms ecosystems and infrastructure. Ozone depletion increases harmful UV radiation, causing skin cancer, cataracts, damaging plants.
And climate change, melting ice, rising sea levels, coastal flooding, more extreme weather, droughts, floods, shifting habitats, famine risk, biodiversity loss.
So, management strategies. Reducing our carbon footprint is the overarching goal. Using less fossil fuels, switching to renewables, improving energy efficiency.
Carbon capture and storage technologies, smarter transport policies, public transport, cycling, electric vehicles, maybe congestion charging.
International agreements are vital, like the Montreal Protocol that phase out CFCs and the Kyoto Protocol and Paris Agreement on climate change.
Catalytic converters in cars reduce harmful emissions. Flue gas, desulfurization, scrubs sulfur from power plant emissions. Reforestation helps absorb CO2. Taxation can incentivize cleaner choices.
Okay, Chapter 8 takes on human population dynamics.
How populations are distributed, often clustered near coasts, lower density in deserts, mountains. Density is people per area. Distribution is the pattern of spread.
Population growth often follows that S-shaped curve slow lag phase, rapid exponential growth, then leveling off at the carrying capacity.
Population changes are driven by birth rates, death rates, and migration. Natural increase is birth minus deaths.
Migration is influenced by push factors driving people away, poverty, conflict, environmental problems, and pull factors attracting them elsewhere, jobs, services, safety.
The demographic transition model describes how birth and death rates typically change as a country develops.
Population structure, the mix of ages and genders, is shown in population pyramids.
LEDCs often have wide-base pyramids, high birth rate, young population. NEDCs tend to have narrower bases, wider middle stops, lower birth rate, aging population.
We talk about dependent populations, young and old, versus the independent or working age population.
Managing population size involves strategies like family planning programs, improving health and education, especially for women, which tends to lower birth rates, and sometimes national policies encouraging or discouraging births.
Finally, Chapter 9 dives into natural ecosystems and human impacts on them.
Defining key terms. Ecosystem, community plus environment. Population, one species. Community, all species. Habitat, where an organism lives. Niche, its role.
Biotic living components. Producers, plants, consumers, herbivores, carnivores, decomposers, bacteria, fungi. Abiotic, non-living factors. Temperature, water, light, oxygen, pH, salinity. These determine what can live where.
Interactions like competition for resources, predation, pollination are vital.
Energy flows through food chains and food webs from producers up through trophic levels. Only about 10% of energy transfers from one level to the next, limiting chain length. This is shown in ecological pyramids.
Respiration releases energy. The chapter also mentions major biomes like tundra, taiga, rainforest, desert, savanna, large ecosystems with characteristic climates and life forms.
Human activities cause major habitat loss during wetlands, converting land for intensive farming, deforestation.
This leads to loss of biodiversity, the variety of life and genetic diversity within species, increasing extinction risk.
Deforestation is a huge issue. Causes include logging for timber, clearing land for farming, subsistence or commercial, building roads and cities, mining, gathering fuel wood, making furniture and paper.
Impacts are severe. Habitat loss, soil erosion, desertification, silting of rivers, displacement of people, contribution to climate change, loss of potential medicines from forest plants.
Which is why sustainable forest management is so important. Forests store carbon, regulate water cycles, prevent erosion, harbor biodiversity, provide resources like timber and medicines, and support ecotourism.
How do we measure biodiversity? Sampling techniques are used. Quadrats, square frames, for counting plants or slow-moving animals in a defined area. Transects lines to see how species change along a gradient. Random sampling helps compare areas fairly. Systematic sampling is used along gradients. Quadrats and transects are relatively quick and cheap, but need careful use to avoid bias.
For mobile animals, things like pitfall traps for ground insects or pooters for gently collecting small insects.
Conserving biodiversity requires many approaches. Sustainable harvesting of wild resources, like medicinal plants, based on understanding their populations.
Sustainable forestry practices like selective logging. Agroforestry combining trees and crops.
Protected areas like national parks and wildlife reserves need effective management and enforcement. Habitat corridors to link fragmented areas. Extractive reserves allowing local communities sustainable use. World Biosphere reserves with different zones for protection and sustainable use.
Seed banks to preserve plant genetic diversity, especially for crop wild relatives. Zoos and captive breeding programs for endangered species, focusing on genetic diversity.
And a sustainable tourism, or ecotourism, that minimizes impact and supports conservation efforts.
It's amazing pulling it all together how interconnected everything is from these 9 chapters.
Absolutely. You see how rock and mineral extraction in Chapter 1 fuels energy needs in Chapter 2, which impacts the atmosphere in Chapter 7.
Which affects agriculture in Chapter 3, water in Chapter 4, oceans in Chapter 5, natural hazards in Chapter 6.
And ultimately the ecosystems in Chapter 9, all driven by population dynamics from Chapter 8. It really is one big system.
It is. Well, this deep dive has certainly given us, and hopefully you, a solid overview of these foundational environmental topics and how they link together.
From geology to ecology, it emphasizes the need for that integrated approach to managing our planet.
Definitely something to reflect on. We hope this has sparked some further curiosity for you in the specific areas.
Indeed. It's complex, but understanding these connections is the first step.
And maybe a final thought to leave you with. Reflecting on all these interconnected systems we've discussed across the chapters, what's one surprising link or maybe an unexpected consequence that really stands out to you about our relationship with the planet? Something to think about.